Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new topic regarding the diameter of nozzle for maximum transmission of power through nozzle. So in our last video lecture, already have discussed the fluid flow through nozzles, as well as we have discussed about the power transmission through nozzles also. And also we have discussed the maximum transmission of power, what is the condition is there, that also we have discussed. So here we'll identify what is the diameter required of a nozzle for maximum transmission of power through the nozzle. So before going to derive this equation, let me give a brief information regarding the diagram, how it is. So actually this is the tank is there, or big reservoir is there, and from this tank the liquid supposed to be flows through a pipe, and at the top of the pipe we have a connection of nozzle is there here. So this nozzle is connected to this one, okay, and this tank is filled of liquid. It may be any kind of liquid here. So and this is the entry part of the pipe. So the pipe length is L, the length of the pipe, and this is the diameter of the pipe D, and the velocity which is flowing through this pipe, like this, the liquid which is present here in this tank, it's supposed to be flows through the to the pipe through this inlet part. Okay, so this is the inlet, and this one we can give a name of tank, and this is nozzle part, and the small d is the actually the diameter of the nozzle, and the velocity which is coming out from this nozzle is small v, and the fluid which is flowing through this pipe, that is capital V. Okay, so these are some terminologies will be used here, and the head present at that inlet of the pipe, that is capital H. The head present at the inlet of the pipe. So these are things, the basic details regarding the diagram. Now from here we have already derived the maximum transmission of power. What is the condition required for that? Now we got in the previous lecture that HF equal to H by 3. At this condition, the maximum power transmission will be done. So HF is nothing but the head loss due to this friction in this when it is flowing through the pipe, which is equal to H by 3. H is nothing but the head, total head at the inlet of the pipe. So 1/3 of head, this one. Even we also know that, also the HF equal to the value is 4FL V square by 2dg. This is the equation we know already previously. This is the major loss, or the loss of head or loss of energy at the inlet of the pipe, and this is the outlet part. So if you write this value in this equation, just you can get it a new value like 4f lv square by 2dg, and this is h by 3. So now if I want to write the value of h, so I can write h equal to, just to multiply 3 into 4f L v square by 2dg. Okay, now even we also know that the h equal to, the h is as I told you, this is the total head at the inlet of the pipe. So also we know that the h equal to the total, this is at inlet part. So let me write, this is also we can write the head at the inlet condition is equal to the head at outlet of the nozzle, this is outlet of the nozzle, plus the loss of head while flowing through the pipe, HF. So the head at the outlet condition, we know that this is kinetic head is there, because the total energy is converted to kinetic energy while actually the when the liquid is flowing through the pipe, all the energy, like means pressure energy and kinetic energy, both will be, you know, formed in terms of kinetic energy when it is coming to the nozzle. So the liquid which will come out from this nozzle only in terms of kinetic energy, that means in terms of high velocity. So because the pressure energy also converted to kinetic energy at this nozzle part. So at this outlet of this nozzle we'll get the kinetic head. So what we can write here, kinetic head equal to, we know that v square by 2g. So v square by 2g plus hfl, we can write the same thing, like 4f lv square by 2dg. So now what we'll do, just mark it equation 1, and this one we can give equation 2. Now both are everywhere. Here also H inlet, this is also H inlet, and here also H inlet. Now if you equate these two equations, now let's write equate equation 3, sorry, equation 1 and equation 2. Equation 1 and equation 2. So we can write 3 into 4fl v square by 2dg equal to, this is v square by 2g plus 4fl v square by 2dg. See, in the both side is same thing, is that 4fl v square and 2dg, this is also 4fl v square by 2dg. Anyway, just to multiply this one, we'll get 12. What we'll write here, let's keep this v square by 2g one side, and other side will be 3 into 2, this is 12 fl v square by 2dg, and this term let's take it to the other side, so it will be minus, that means minus 4f lv square by 2dg. So what we'll get here, v square by 2g equal to, we can write here v square by 2g equal to, we can write 8fl v square, 8f lv square by 2dg. This is equation 3. Let's give this equation 3. Okay, now this is one equation. Now we know that actually one more term is there, that is continuity equation. From the continuity equation we know that AV equal to AV, like means A1 V1 equal to A2 V2, or we can write AV equal to small av equal to capital AP. What is small av? The area at the nozzle, and V, the velocity of the fluid which is coming out from the nozzle, that is AV, and capital AV equal to area of this pipe and velocity of the fluid which is flowing through the pipe. So here what we can write? We can write this velocity equal to capital V equal to small av by A. Now just put this value in this equation. So what we'll get here? So let me write in the next slide. So here just put the value of AB there. So what we can write? 8FL, and in place of V, this one we can write AB square. This is 2DG, and here A square. And in the right hand side we can write V square by 2G. V square by 2G. So now if you see both side V square by 2G is there, let take a common on that, or we can do one thing, just to cancel this V square by 2G both side. So what we'll get here, V square by 2G, V square by 2G will be cancelled. So what we'll get? 8FL by D, and here we'll get A square by A square equal to, this side already is cancelled, so we can write 1. Or else we'll do one thing, just you divide V square by 2G in both side, that also you can do. So this is equation 4. This is equation 4. Now this A square by small a square by capital A square, just put the value of this area in terms of diameter. So we can get 8FL by D, and this one we can write pi by 4. This is small d square because area of the nozzle. Here also similarly pi by 4. This is capital D square, area of the pipe. So this one we can write equal to 1. And now this pi by 4 will cancel. So we can write this is a square is there. So a equal to this one pi by 4 d square. Again square means it will come d to the power 4. Here also same thing, d to the power 4, because a square is there. So I have just written the value of a, pi by 4 d square. Again square means d to the power 4 will be there. Now again one more line we can write it like 8FL by D into this one we can write just D4 by capital D5 equal to 1. Now I'll write the value of d to the power 4 equal to, I'll keep this d to the power 4 one side, remaining term I'll take it to other side. So this is d to the power 4, this is d to the power 4, again d is there, so this is d to the power 5 divided by 8FL. Now we need to find out the value of diameter of the nozzle. So d equal to, small d equal to what we can write, capital D to the 5 8FL to the power 1 by 4. This one we can write, and this give this equation 5. So what is our motto was there? The diameter of nozzle. So diameter of nozzle I told you, here it is, the small d is there, and so finally we got this small d equal to d to the power 5 by 8FL to whole to the power 1 by 4. Okay, so again we have seen in the previously, like from equation 4 we can see this, like this equation is there, and we can write this value. How we can write this in terms of let's take it to a square to other side. That means from equation 4 we can write one more things like 8FL by D equal to this a square by a square, take it to the right hand side, so we can write a square by a square, and finally we can write capital A by small a. Let's take this root over part and keep it the other side, that is 8FL by D. This one give equation 6. Okay, this is also one part. Here if you see this equation which gives the ratio of area, which area? The area of the pipe, the fluid which is flowing through the pipe to the area of the nozzle here. Okay, and if you see here, now this is the area of the pipe and this is the area of the nozzle part here. Okay, so this equation gives the ratio of area of the pipe to the area of the nozzle, and from this equation also we can able to identify the diameter of nozzle, also can be calculated from here, or else we can calculate from here also. Both the equations are there, the same thing, same concept will come, like same value we can get it from both the things. So I hope you understand how to identify the diameter of nozzle for maximum power transmission from the nozzle, through the nozzle. So these are the equations what we have derived previously for the condition of maximum power, for the maximum power transmission of power, what is the condition required. So there we got HF equal to H by 3, and from there we have started our equation. This is our major loss equation or head loss equation through the pipe, and finally we got this equation, D equation, and from this equation also we can able to calculate the value of diameter of nozzle. So I hope you understand this theory concept of this diameter of nozzle for maximum transmission of power. Still, if you are having doubt regarding this, you can give a comment in the comment box. Thank you all.